Hi and welcome to maths class. Today we're looking at area under a curve. And so what you see there is a graph of y equals f of x, and just a reminder of what we looked at in our last couple of videos when we learnt about the fundamental theorem of calculus, that I can find the area under the curve between the point A and B by using this formula, which is the antiderivative of f of x, or the integral of f of x, and then I use a substitution with b and a, and I do a subtraction. So what it ends up looking like is f of b minus f of a, where capital F is the antiderivative of small f. All right, so let's do a quick example. So there's my first example. I want to find the shaded region. So that region is bounded by four lines. There's the x-axis, then there's the line x equals 1, that's a vertical line. There's the line x equals 2, that's also a vertical line. And then there's a curve, which is y equals 2x squared. So I need to find this area. So basically what that means I'm finding is the definite integral from 1 to 2 of 2x squared dx. So all I need to do then is antidifferentiate and then substitute. So let's do it. I antidifferentiate. So my power goes from a 2 up, I add 1, I get 3x cubed. And in front, I'm going to keep this 2 and I'm going to divide by the new power. So that's 2/3 x cubed, and I'm going from 1 to 2. So now I do my substitution. I substitute 2 into x cubed. So that's going to give me 2 cubed, which is 8. Times 2, that's 16 over 3, minus, I substitute in 1, and that's 2/3, 2/3. So 16/3 minus 2/3 gives me 14/3, and that's my final answer. So 14/3 is the area under this curve. Now what we're going to do is look at this straight line graph, and we're going to explore what happens when I use different methods to find the area under the curve. Now this diagram is in your textbooks, but also my students should have this handout. Notice that it does start halfway down the page. So the first thing we're going to do is I've got this line which is y equals x plus 1, and I'm going to start by using triangles to find the three areas. The first area is A1, the second area is A2, and the third area is the sum of the two areas. Okay, go ahead and do that, and then pause and I'll show you what to do next. Now I want you to use the fundamental theorem of calculus to find the same areas, A1, A2, and A1 plus A2, which means that if we've got the function y equals x plus 1, I'm going to antidifferentiate that function. You're going to get some interesting answers, so I want you to think about what you conclude, and then I want you to think about how can we use integrals to calculate the shaded area. Now for a triangle we don't need integrals, we can just use the triangle formula, but obviously later on we'll be doing formulas for which we won't have a straightforward formula. So if I needed integrals, what would I need to do to get the correct area? So you go ahead and do that, then hit pause, and I'm going to go through it all. Okay, there's my working out so far. So what you can see is I've calculated A1, which is going to be a half times the base times the height of that right-angled triangle, and I get 9 over 2. Then I calculated A2 just here using the same method, and I got a half. So when I add the two areas together, 9 over 2 plus a half gives me 10 over 2, which is 5. Let's do the second part. So there's my working for the second part. I'll just go through it. For the first area, I calculated the antiderivative of x plus 1 from -1 to 2. And so I got x squared over 2 plus x, again from -1 to 2. So when I substitute then, I get x becomes 2, so that's 2 squared over 2 plus 2. And then I subtract when -1 is substituted. It's -1 squared, which of course will become 1/2. minus 1. So this 1/2 minus 1 is negative 1/2, but I'm subtracting it so it becomes positive 1/2. And of course this part here simplifies to 4. This is 2 plus 2 becomes 4. So I've got 4.5 there. Now that is the same as what I got on the previous page. For area 1, I found 9/2, which is the same as 4.5. All right, let's look at area 2. Now remember that for area 2, I got an answer of 1/2. So I go from -2 to -1, the antiderivative of x plus 1 dx, same antiderivative. I substitute in -1, I still get -1/2. I just used what I had already discovered there. -1 minus, now I substitute -1, so I get 4/2 minus 2, so that's 2 minus 2, which is 0. So my answer is -1/2. Now let's compare that. For the second area, let's have a look at the diagram. Oops. Here's area 2. So when I just calculated the area using my knowledge of triangles, I got 1/2. But when I used calculus, I got -1/2. All right, now let's look at the sum of those two. A1 plus A2, I didn't add these together, although if I did, I would get 4, not 5, which is what I got on the other side. So I go from -2 to 2, so I substitute in 2 into here, which gives me the 4 again. I substitute in -2, that gives me 0. So 4 minus 0 gives me a total area of 4, which is not what we expected, okay? So what do you conclude, and how could you use integrals to calculate the shaded area? Have a think about those questions and see if you can come up with an answer. Then I'm going to take you through what we do. So let's have a look at it. What I've got here, my total area, which is 5, if I wanted to use integrals, I would need to calculate A1 minus A2, because A2 gave me a negative value. Now, of course, an area can't actually be negative, but because it's below the x-axis, my calculations produce a negative value. So that means that in order to get the correct area of 5, I need to do A1 minus A2. So I do that by going from -1 to 2 of f of x dx minus from -2 to -1 of f of x dx. I need to kind of do it twice, basically. Now, if I didn't do that, then I'm still calculating a real thing, but it has a different name, and it's called the signed area. Now, the signed area is not the actual area. It's going to give us the total when I add and subtract the positive and negative parts. So if I calculate from -2 to 2 of f of x dx, I'm going to get 4. So I won't get the same answer as if I actually want the area under the graph. So, there it is. Okay, so we've got the signed area under a curve versus the actual area. So in the diagram that I've drawn here, this is a function y equals f of x, and I have an interval from a to b, and I want to calculate the area under the curve. So if I calculate the integral from a to b of f of x dx, I'm going to get the signed area. This is not going to give me the actual area. On the other hand, if I want the actual area, I'm going to need to add together the red bits and subtract the green part, because the green part is below the x-axis and it'll give me a negative value. So I subtract it to make it positive. So the actual area is going to be this. I'll go from a to c, f of x dx. Then I'll subtract from c to d of f of x dx. And then I'll need to add from D to B of f of x dx. And each time you see an integral of this kind, you're going to have to think, well, where does the graph cross the x-axis? Because if I need to calculate the area, then the area under the curve is going to give me a negative value. So now we're going to work through this example together. We have a graph there, y equals, that's x cubed minus 4x. Sorry, that's not terribly clear. And the interval we want is from -2 to 2. We want the shaded area, so it's from -2 to 2. But I can see that from -2 to 0, the shaded area is above the x-axis, and from 0 to 2, the shaded area is below the x-axis. So your first question is, express the shaded area as a definite integral. Okay, so pause, and let's do that first. We're not evaluating it yet, we're just writing down the integral. Pause it, and then watch what I do. Okay, hopefully you've done it now. So I'm going to make, this is my positive signed area here. I'll call that A1, and this is my negative signed area, A2. So the shaded area in total, I'm going to want to calculate A1 plus A2. I'm going to need to do the integral from -2 to 0 of x cubed minus 4x dx. And then I'm going to subtract the integral from 0 to 2 of x cubed minus 4x dx. That's part A. I've expressed it as a definite integral. Now it says a definite integral. This is actually the sum of two definite integrals, or the subtraction, the difference. It doesn't have to be one definite integral, all right, but we wanted it to be the two shaded areas. Okay, now I'm going to calculate the area. So just pause it, do it yourself, and then come back to me. Okay, so there's my solution. I've anti-differentiated x cubed minus, or you can't see that, x cubed minus 4x to get x to the power of 4 over 4 minus 2x squared. And then I've put in my terminals from -2 to 0 and from 0 to 2, and I subtracted because this one is subtracted, the second one. And then I just have to do my substitutions. The 0 is easy because this is a polynomial, so when I substitute in x is 0, I get 0. This becomes 4 and this becomes 8, so I have 4 minus 8. Because of course this is negative, but these powers are both even. So what I end up with is I have symmetry here and I get the same solution here. So I have 4 plus 4, which equals 8. Now this suggests to me that my original graph, in fact, has rotational symmetry here, and that area 1 equals area 2. Now, if this is a function like a sine function where you know that's going to be true, you can use that fact. But we weren't certain here, although they look very symmetrical. I wasn't going to trust the fact that it looks symmetrical to be quite certain that it is symmetrical. Although by the time I'd realized that I had only even powers here, I realized that that was going to happen. Okay. So just to recap, when we're looking at using integrals to calculate areas, we have to remember that if I just use the integral over the entire interval, that's going to give me the signed area. And if my graph crosses the x-axis in between A and B, then that's not going to give me the true value of the area under the curve. Now, if the question asks you to calculate this integral, then that doesn't matter. You calculate this integral. But if the question asks for example, the shaded area, it doesn't mean the signed area. It means this plus this plus this, making this positive because it's an area. And then we have to use the technique of subtracting all regions that are below the x-axis. And that's the end of the video on area under a curve.